Okay, so first off, what we're going to do is we are going to take a look at the answers to the task that I set you in the last lesson. And these kind of questions are going to come up. You're going to need to get pretty good at them, but we're going to be doing them throughout the whole year. So I don't actually want to overdo them at the moment. We're going to keep coming back to them, and you will hopefully over the course of the whole year develop a really good mastery of these questions. So what we had was we had 3 moles of sugar dissolved in 10,000 milliliters of water. I hadn't actually written water, but I meant to write water. What is the concentration of the solution? So what we've got is our equation from the data booklet, which is N equals CV. Now, I know that I want that one because I'm being asked for the concentration. So I'm really being asked what this one is. What I want to do with that is convert it into a little triangle. So I am going to have concentration and volume in the bottom and number of moles in the top. I'm just going to make that an M to make it clearer. Now, I have been told what the moles are, and that was 3. And I have been told the volume, it was 10,000 milliliters. Now, what I want to do is convert that into litres, so I'm going to divide it by 1,000. So I'm basically just going to do that. And so what I've got is 3 divided by 10 equals 0.3 moles per litre. And remember, you can have that unit as a dash, but not both. So it's either -1 or a dash, but not both. So that was the answer to question 1, and that's how you did that one. Now, the next one that we've got is, once again, we've got N equals CV, and this one's asking me about lithium chloride, and I've got 20 kilograms of that lithium chloride and 5,000 litres of water. What is the concentration of the solution? So I do have my volume. I'm being asked about my concentration, but I do not have my number of moles. So that causes me a bit of a problem. But I do have the mass, and I have the compound that I'm looking at. You will have to be given that information, and they could set up the question where you just need to know that and figure it out yourself. So to find out what the number of moles I actually have is, I have my equation moles equals mass divided by the gram formula mass. So the mass that I've got here, I actually need to be careful with. That mass is, well, when I convert this into my triangle, M for mass, I'll write mole there, GFM. What I need to remember is I've been given 20 kilograms, and all these equations are done in grams. This will help you because it's gram formula mass, which means this needs to be done in grams. Now, that means that this needs to be multiplied by 1,000. We will go over how to convert units, but if you are going down a unit, you're going to have to increase the number of zeros because that K represents those 3 zeros. So that's actually going to be 20,000 grams. And the GFM is going to be derived from our lithium chloride, and our lithium, if we take a look in the data booklet, should hopefully be, it's 6.9 in this one, I think it's 7 in yours. So 7 plus 35.5 gives us, mental arithmetic, 42.5. Now, what we need to do is to find out the number of moles, we're going to need to take that 20,000 and we're going to need to divide it by 42.5. So, I do that quickly. That gives me 470.58 moles. So that equals 470.58. Now I'm not actually, in fact that would be 9. I was rounding. What I'm not going to do is actually change it yet. I'm going to leave it in my calculator and I'm going to use that number that's in my calculator. So now I do have the number of moles, and the number of moles I've kept in my calculator, and it is 470.59 moles. Now what I want to do with this one is I want to take that and convert it into my triangle. CV moles. I do know what my number of moles is now. It's 470.59, but I've kept it in my calculator because if you keep rounding it too early, you sometimes skew the end number enough that it's out with the tolerance. So don't round until the end. I do have my volume. My volume in the question was 5,000. It's been given to me in litres, so I don't need to deal with that. So that is going to be 470.59 divided by 5,000, which equals 0.094 moles per litre. And that's my final number. And what I didn't do in the first one, and what you should do, is double underline it. So that's my final answer. It's a bit mucky. The marker I might be worried the marker might mark the wrong thing as my final answer. Double underline. So those are the first two questions. The last one that we've got is 2 grams of calcium carbonate being dissolved in 50 millilitres of water. What is the concentration? So once again, I've got my concentration equation from my data booklet. I am looking for the concentration once again. I do have the volume, but I don't have my number of moles, but I do have my mass, and I have the formula for the compound that I'm talking about. So this time what we've got is we've got our moles equals mass divided by GFM, which we can convert quite nicely into our triangle. Trust me, the more times you do this, the better you get at it, and it is something that if you've got a system and you keep using the system, it will pay dividends in the long run. So my mass that I've been told about is 2. My GFM I'm going to need to work out. So I've got calcium, I've got carbon, and I've got O3. Ooh. So my calcium from memory is about 40 plus 12. Now this is important. We have 3 oxygens, so that is going to be plus brackets 16, which is the relative atomic mass of oxygen, times 3. So what I want to do is plug all that in. 40 plus 12 plus brackets 16 times 3. And that gives me GFM of nice and round 100. So my number of moles is going to be 2 divided by 100, and really, if I put these zeros up there, I think that's it. But what I want to do is 2 divided by 100 in my calculator. Oh, it's 0.2. Now, I just made a silly mistake, and I checked it on my calculator before I went any further, because I made just a wee silly mistake there. I put 2 zeros instead of 1 in front of the 2, and I checked it in my calculator. It's a simple thing. It's a really simple thing, but you're in an exam. You're under stress. So that 2 divided by 100 is 0.02. Really important that you check it. Really, really important. Everybody loses marks. Just make sure you check. Just make sure you check. Right, so we've now got our number of moles. We can tick that off there, and that is 0.02. Our volume from the question was 50 milliliters. So what I want to do is I want to convert this into my triangle so I can see things clearly. I can tick things off. Oh, now will I risk doing that again? No. I won't embarrass myself again. 0.05. I suck at counting those numbers. I need to get better at that. So, for my concentration, it's just going to be 0.02 divided by 0.05, which is 0.4 moles per litre, and double underline it. Use your calculator. I make mistakes all the time, and could have edited the video that I didn't make that mistake. Could have made it deliberately. You will never know. But it is important that you use your calculator to check, especially when you're in the exam. Lots of zeros, lots of numbers flying about. Easy divisions seem harder when you're under stress. Just take your time. Use the calculator. Lower the stress on your working memory. Right? Now that we've got the task answers, I'm going to move swiftly on to complex ions, and then we're going to do a little bit on pH today. It'll be quite a heavy one because I did not get round to pumping much out yesterday. You got some quizzes on Teams, but it wasn't really very much. And I want us to keep going. I don't want to push too far, because I don't know how things are going to look, and we are actually making some relatively good pacey headway, to be quite honest, but we do need to move on to pH, and I think the next little bit is quite interesting, and it'll open us up to doing some questions, and hopefully before too long having some actual proper chats about what's going on. So we will start on complex ions next. Right, any notes to take will be on the white bits of paper, so these should form your notes for this lesson. The complex ions are actually really an interesting way of thinking about things. They're basically a molecule that has a charge that is going to remain as it is through most equations. Now, you can break these ions up, but the way that we're using them, especially in the reactions that we're using them in, we treat them as singular objects. So that'll become clearer as we speak about it. And it's really important that you get to grips with not finding these complex, because it's actually really quite straightforward. You get a list of all the complex ions that we use in the data booklet, and you can just flick to that data booklet and it tells you everything you need to know about those ions. I'm going to go into a little bit of depth after we've taken a look at the data booklet page, I'll talk you through that a little bit. I think it'll be better if it's actually on the computer screen and I record it from there, just so that we can see it clearly. And you will constantly have to go back to that. You're not in any way required to remember it. You will start to build up a memory bank of what the complex ions are, and that will help, but it's like, for the time being, you're using the data booklet. It'll take you a couple of years to really get fluid with it, and even now, it's honestly not something that I want to realise I've made a mistake with halfway through a question, so I tend to double check in the data booklet that I've got everything right. The data booklet's really going to tell us two things. It's going to tell us what the complex ion is made up of and the valency, and we can use that valency to decide how it's going to react with things, and it has a really big impact on the pH that we get from different compounds. So that's your note for it. We'll take a look at the data booklet.
Okay, so in the National 5 Chemistry data booklet, we will, if we scroll to the contents page, we will find, hopefully, our formula of selected ions containing more than one kind of atom. So these are our complex ions. So if we scroll down to page 8, this is page 8 here, so we've got our solubility stuff here. Now these are our complex ions. We've got one positive complex ion, which is ammonium, which we will come on to later on in the course. We've got our one negative, so these all have a valency of 1. So you would draw brackets around your molecule here, and you would put a valency of 1, and you would swap that across if you were working out what your molecule was going to look like, and we'll take a little bit of a look at that later. We've got our two negative ones, and interestingly we've got this sulfate ion here, and we'll be going through a little bit more of that. So these all have a valency of 1, valency of 2, valency of 3, and you'll find that on page 8 of the data booklet.
Right, so I want to cover two little complexities, and then we'll re-simplify this whole thing, because actually it is pretty straightforward when we disregard there's stuff we don't know about what's going on, and we'll go into that. So if you take the valencies for sulfur and oxygen, what you'll find is you get a ratio of 2 to 2, which you can simplify to 1 to 1. So actually this should just be, if you're using valencies, one sulfur atom and one oxygen atom. The sulfate ion, because it doesn't have that ratio, is going to create a charge, and the charge is 2 negative. We don't need to worry about how this forms, or why sulfur with a valency of 2 has 1, 2, 3, 4, 5, 6 bonds attached to it. We're not worrying about that. That stuff comes a lot later, and you can just know for the time being that the valencies do work. They are sensible and they're good things to use, but they don't always hold true. And you will learn about that actually probably after Advanced Higher. So this is really pushing things quite far into the future. So I don't want you to get worried that this is weird. It is weird. You don't know why this looks like this. You don't know how this forms. It doesn't make sense with the rules as you know them at the moment, but it doesn't matter. We're gonna package all this nightmare back up, and we're going to send it into the future. And you can unpackage this nightmare when you do, I think it's expanded octets at first year of uni. So someone smarter than me can teach you all about that. So what we've got is this sulfate ion. We've got a sulfur atom and we've got oxygen atoms. The whole thing has this 2 negative charge, and I've put those brackets around there to just highlight that this always stays like this. It's not gonna break apart in any of the questions that you're given. So when you see a complex ion, it's gonna stay as that complex ion for the entire question. It's not gonna morph, it's not gonna take part in a reaction other than binding to something as its whole self. These oxygens are not coming off this sulfur ever in National 5. So this complex ion is treated as a singular thing. So that hopefully is us starting to understand complex ions. What I'm going to add in next is a little bit of pH, and we're going to come back to these complex ions and we're going to see how that plays out. What I will put in your heads is, in fact, no, we're just going to do the pH first, then we'll come back to this. I don't want to get us confused. So next up, a little bit of pH. Okay, some really key definitions, and actually I want to explain this as clearly as possible, because it's something that you're going to be asked about. They ask about it every year. It happens every year. There is questions based upon this. The entire crux of this key area depends on your understanding of the next 2 bits of paper. So if you can get this down, you will nail this pH stuff. It will take you a while. There's still a couple of complexities to it, but generally speaking, if you know the next 2 bits of paper well, you are on very solid footing. So an acid is okay, so we are going to have a little play around with our absolute classics, which is our hydrochloric acid, which is HCl, a hydrogen and a chlorine combined, and sodium hydroxide, which I should have mentioned this before actually. This is 2 atoms that are in a molecule that is charged. That is a complex ion, and you will deal with that OH negative as something that does not break apart. That oxygen's you're never gonna see that leave that hydrogen. You're gonna deal with that as a single component. So what we're gonna do is we're gonna mix these 2 things together, and we're gonna see what happens, and talk a little bit about an experiment that hopefully we will get to do at some point. So as we put that HCl into water, it has the ability to dissolve, and it will dissolve by breaking apart the bonds that hold the hydrogen to the chlorine, and we are going to get chlorine, Cl negative, and hydrogen, H positive, floating in that solution. Now, what have I turned this solution into? Well, I have increased the concentration or the number of H positive ions. So this is currently now an acid. So this is an acidic solution. If I tested it with pH indicator, it would go red. Now, if I add in my sodium hydroxide, that will also dissolve in the water. I'm going to get this OH negative, and I'm going to get this Na positive. So what's going to happen here is that the H positive ion and the OH negative ion are going to bond together. Now, what that will do is simply make another water molecule. So if I add that OH negative ion in, it's going to bind to the H positive ion, make water. The substance is now neutral because I've removed that H positive ion and I've bound it to the hydroxide ion and it's become water. Now, what we are left with is our spectator ions. And these have not changed in any material sense during this reaction. So the sodium and the chlorine are still present in the state that they were in before the reaction took place as they are after. So there has been no actual change to that. Now I can represent this as a chemical equation, and I want to do that so that I can take you through exactly what's happening. So these spectator ions are actually quite important, because what we can do is we can add heat here and we can evaporate all that water off. And when we do that, these, once this evaporation has taken place, will form a salt. Now, this is actually a really interesting thing. All neutralization reactions will form a salt, and you will have to be able to identify that salt and possibly name it as well. So we're going to take a look at the chemical equation to this, and then we are going to have a little go at something a little bit trickier. So the equation we've got is going to be HCl. Now I'm going to put the state symbol AQ. That means this is already in an aqueous solution and it's dissolved. Now I'll speak a little bit more about this going forward, but essentially that means that these are already in the form of ions. Plus NaOH EQ. You'll often see that with brackets because remember that hydroxide is a complex ion. This will then form NaCl plus H2O. That'll be a liquid, and this will be aqueous until we evaporate the liquid off, and then it'll form a solid. So this is our salt that we form, and that's the chemical equation that you'll probably be given in a question, and we'll build up to tackling some questions with those a little bit later on. What you'll notice is the Cl and the Na are, forgot my brackets around my state symbols there. The Cl and the Na have stayed as ions, and they are still aqueous after this reaction's taken place. So they have actually been spectator ions. So those are considered spectator ions because they haven't taken part in the reaction, in terms of they haven't undergone any material change themselves. Right, we're going to do our tricky example next. Okay, so let's tackle the complex ions with pH, and then I'll set you a task and you can stop listening to me gabber on. Right, so what we've got is the SO4 2 negative ion. Now, I'm going to put the valency as just 2. It is 2 negative, but I'm not going to worry about that too much at the moment. Now, if I pick something like magnesium, that has a valency of 2. So if I want to know what magnesium sulfate, what that molecule is going to look like, all I need to do is swap the valencies over. Now notice that the valency jumps the entire bracket. So that complex ion is put in the bracket and I get Mg2SO4 2, which can then be simplified because these are just ratios to MgSO4. And that is my molecule for magnesium sulfate. Now, if I have hydrogen, what's going to happen here? So I've got hydrogen, which has a valency of 1. I've got my sulfate complex ion with a valency of 2. I want to swap these over and I get H2SO4. That is you might see it with an F. I use a PH. I think the British is PH, the F is American. It could be the other way around. I don't care. I can barely spell at the best of times. That'll do. So, we have got sulfuric acid. Now, if we compare HCl to H2SO4, we'll notice something quite interesting. Here, in this molecule, when this breaks up, I just get 1 H positive and 1 Cl negative. When this breaks up, aka when it dissolves, I will get 2 H positive ions and an SO4 2 negative ion. So that is going to impact things going forward. And you've got a bunch of complex ions there in that table that can contain, I think, potassium oxide has a valency of 3. I can check it. Not just guess. So our phosphate ion has a charge of 3 negative. So that's the only one that would have 3 hydrogen ions attached to it. So if I was to put 1 mole of HCl into a cup of water, I would get, and then I would get whatever number. Say we put 100 molecules of HCl into water, I'd get 100 H positive ions. If I put 100 of my sulfuric acid in, I would get 200 H positive ions. Now that means that sulfuric acid has got double the equivalent strength of hydrochloric acid. It's why at school we tend to use hydrochloric acid a lot more than we use sulfuric acid. Sulfuric acid's just nastier. It's got more H positive ions. It's going to give you a greater level of acidity. In fact, it will have double the level of acidity that the equivalent amount of hydrochloric acid would have. So, I think I'm going to stop there. I think that was quite a lot. What I'm going to do is set you a task and we will do another lesson on Thursday that will be pretty similar, and I will go through some more of the pH stuff, and we'll take a look at the kind of salts, some of the sulfate salts that we can get as well. So I'll set you a task for today, because I think that was quite a lot, all at once to throw at you, and Thursday we'll have our next lesson up. Let me know, either on Teams or via email, if the work's either too much or you're looking for some more stuff. I'm going to be putting up notes. We're going to have a class notebook with notes in it that we can all have access to, and that'll be on Teams. A lot of this will continue into next year, it seems, so we will have to talk about things, and we will have to see how things change going forward. The people that have been putting stuff in have been doing fab. If you've been struggling, that is more than okay. It has been a long time since anyone had any sense of normality, and all the stuff you need is in the YouTube videos. So if this is the first lesson that you've come to for a while, they're up there and they're not going anywhere. I will put them once the summer kicks in. I will put them into playlists so they're in order. It's a good idea to look back at them and to keep refreshing your memory. We'll do loads of revision when we all come back together anyway. So just hang on in there and enjoy doing the task.